In this video, we're going to be talking about messages, how to understand their definitions, and how to create your own custom message types in your ROS packages. We've already talked about how ROS messages are structured chunks of data that get sent across topics, but we haven't seen how the structure of those message types is actually defined. Well, that message structure is defined in message files inside of packages. A good resource for starting to understand how these files are laid out is the ROS Wiki. Here on the Wiki page that describes the message file format, we can see that every line defines a new field, with the first entry in that line being the type of the field and the second entry being the name. And the example they give here is two 32-bit integer fields called x and y. Now you might be wondering what field types are available, and that's what this next table tells us. Pretty much all standard data types are represented here. We have everything from booleans through different sizes of integers, different sizes of floating point numbers, strings, and special field types for time points and durations. This table also tells us how those types are going to be represented when they're decoded into C++ and into Python code. Further down, we see how we handled both fixed and variable length arrays in messages, because messages can have field types that are arrays. And again, we can see what types those arrays will get translated into when they're decoded in C++ or Python. So that's a good reference to keep in mind when you need to double check what field types are available to you when writing a .message file. Now let's open up the message files for a couple of message types we've used already and see how they're actually defined. Let's open up a terminal, source our setup script, and I'm going to ROS cd into the std messages folder. And we're going to take a look inside of the messages folder within that package at the string.message file. And here we see the message definition for our string message. Perhaps unsurprisingly, this standard string message only has one field, its name is data, and its type is string. So when we were writing our C++ code in the last video and we kept doing message.data, this is where that data name came from. When ROS decodes a message into the message type for objects built into the language libraries, it gives it those members based on the field names of our message file. Now, most of the standard messages only have one field type in them, so they're not terribly interesting. So let's take a look at one of the message types we used when we were working with TurtleSim. In this case, we're going to ROS cd into geometry messages. And in the message folder there, we're going to look at the twist message, which we used when we were instructing the turtle on where to go. We can see that this twist message type has two fields in it, linear and angular, and the types of those fields are vector3. But vector3 isn't in any of the standard message types that we saw on the wiki page. So where's that coming from? Well, the type of message fields can themselves be other message structures. So in this case, vector3 is another message type defined within geometry messages, and we're just combining two of them to give us a twist. So we can close this and open up the vector3 message file to see what this message looks like. And here we see that a vector3 inside of geometry messages is made up of three fields called x, y, and z, all of which are 64-bit floating point numbers. So earlier when we were building these messages to publish them, and we were seeing that structure of x, y, z nested within linear and angular, now you can see how that's actually defined. There is one particularly important type within std messages that we should look at. So I'm going to ROS cd back to std messages and into the message folder, and I'm going to open up header.message. The header standard message type is a type that is often included as a field in many other messages because it includes really common meta information about the message. So for every standard header message, we get a 32-bit sequence number. This number usually just counts up by 1 with each new message when a node is publishing it. We get a timestamp of that special time type that we saw on the wiki, and we get a frame ID that tells us what reference frame our data for this message is in. You'll learn more about frame IDs later. But now you know every time you see a message that declares a header field of this type, this is what's contained in the standard messages header. Alright, now you understand how to read message files and the structures they define. Let's talk about how to actually create our own custom message types in our ROS packages. Let's walk through how to create a message type called string with header. It's going to combine a string data field with a standard messages header field, and we're going to go into our talker and listener C++ nodes and change them to use our string with header type instead of the standard messages string type we originally wrote them with. This is going to be a many-step process, but we're going to take it one step at a time. So, to get started, let's go into our RJ Training package. I'm going to open up a new terminal, and before I forget, I'm going to go ahead and source my setup script and go into our RJ Training package. When we create message files inside of a package, they all live in the message folder, which we need to create. So I'm going to make a folder called MSG for message, and we'll go into that folder. And we will create the message file for our new message type, string with header.message. We're going to have two fields. The first is going to be of type std_messages header, and the second is going to be a string type field called data. That's our whole message file for our new message, but there's one thing I want to point out before we're done with it. When we were looking at the geometry messages twist message, we saw that they used vector3, a message type from their own package, and so they were just able to use it without any qualifiers. Because header is not from our RJ Training package, we need to specify the package associated with it, which is why we have this std_messages prefix on the header type. Now we can save and close that, and we need to tell Catkin to actually build this message into code that we can use in C++. To do that, we're going to need to add two dependencies to our package. So we're going to go back up into our package directory and open up our package manifest, package.xml, and we need to add two tags. I'm going to add a build depend tag on the message generation package, and then an exec depend tag on the message runtime package. So with those two tags added, we can save and close our package manifest. And now we're going to crack open our CMake list file so that we can tell CMake that we actually want to build our messages. We need to put our new dependencies in here, and the message generation one is one that we're going to actually be using at build time, so we need to add that to our find package catkin components list. The message runtime is not going to be used at build time, but it's something that other packages will need if they want to use our message. So we need to add that to the catkin package declaration. We're going to add a new argument, catkin depends message runtime. The catkin package directive contains a lot of different arguments that you can give it. Catkin depends is an argument that tells Catkin something very specific. If other packages want to depend on our package, these are other Catkin packages that they will need in order to get our code working. So in this case, because we're defining our own message types, anyone who wants to use our package and use the message types therein will need to depend on message runtime. By adding that to Catkin depends, the upstream packages that depend on us don't need to know that. Catkin will take care of that automatically. Now, in order to actually build our message file, we need to add a little bit more space between find package and catkin package, and we're going to add two new declarations. The first one is going to be add message files. This is going to tell Catkin which files we actually want to build as messages, so we need to give it the files argument and give it the name of our string with header message file. The second declaration is actually going to be generate messages. Now when we call generate messages, we need to give it the list of packages that our message types depend on. In this case, because we're using the header message type from standard messages, we need to add that to our dependencies list. So we're going to say dependencies std messages. And that's all the changes we need to make to our CMake list file to build our message into an actual usable C++ object type. So I'm going to save and close cmakelist.txt, go back up to our catkin workspace folder, and run catkin build. We've successfully built our workspace, although there's no indication that the message was actually built. So we can double check that our message code got compiled by looking in the devel directory and then looking in a include RJ Training. You should see string with header.h. That's the C++ header file that Catkin generated for us based on our message file. The fact that this header file exists tells us that our CMake setup is working. Now we want to go into our talker and listener node and make them use our new message type. So let's go back into our RJ Training package, into the source folder, and open up talker.cpp. The first thing I'm going to do is replace this include at the top to include the new header that we just generated. So that's going to be rjtraining/string with header.h. And then we need to go to our call to advertise and give it the new type of the message we want to use, which again is rjtraining string with header. And then we need to go into our while loop where we create our new message and again replace that message type with rjtraining string with header. Okay, that's all the changes we need to make to our talker node, so we can save and close this and open up our listener node, listener.cpp. We're going to make the same change to the header. We're going to get rid of std_messages string.h and instead include rjtraining/string with header.h. And then in our callback, we just need to replace that type again with rjtraining string with header. That's all the changes for our listener, so we'll save and close that. There's one more change we need to make back up in our cmakelist file. So I'll go back up into the package directory and open up cmakelist.txt. As it stands, if we build our package, it will sometimes work. See, we've defined targets for our talker node and our listener node, and by calling generate messages, Catkin has created a target for us that will build our message code. But CMake doesn't know that there's actually a dependency between those different targets, so it might order them arbitrarily. If it builds the message target first, everything will work fine. But if it builds either of the node targets first, the message code won't exist yet, and that will break everything. So we need to tell CMake that our node targets depend on our message target. We do this with the add dependencies command. So for each node target, we're going to add a line that says add dependencies. We're going to give it target name, talker node. And then instead of specifically depending on the message generation target, we're just going to depend on all Catkin exported targets, just as a convenience. So we're going to give it the argument Catkin exported targets and do the same thing for our listener node. Again, by adding these two lines, we're telling CMake that there is a specific order that these targets need to be built in because our node targets depend on the results of the generate message target. With that change made, we can save and close our CMake list file. Go back up to our top level Catkin workspace directory and run catkin build again. Everything built successfully, so we're ready to go. We can source our workspace setup script and ROS run rjtraining talker node. And we can open a new tab, source all of our setup scripts, and ROS run rjtraining listener node. And we see the same results printing out. So everything is still working. But if I kill this node and instead run ROS topic info talker topic, we'll see that the message type associated with that topic is now our rjtraining string with header. And if we ROS topic echo our talker topic, we'll see that it now has our header information as well as our data. We can see that sequence number counting up, and because we haven't set the timestamp or frame ID in our talker node, those are just left default initialized. But our data still says hello, and we're publishing messages of a new type. And that's all for this video. We've covered how to understand and create message types in ROS. This is actually a more common occurrence than you might think. While there are a lot of standard messages and other even more useful messages defined in other packages, it is often really important to define your own message types with meaningful names for the data members, rather than just relying on those standard message types. Defining your own message types gives your teammates a much better understanding of what data is actually stored in that message than just using a standard int message, for example. Now, adding our own message type to our package was a lot of steps, but you don't have to do those steps every time. Often you'll be adding a new message type to a package that already declares its own message types, so you just have to add your message file to that list in Add Message Files. But that's it for now. In our next video, we'll be talking about the ROS launch system.